Hi, my name is Mohammed and I'm an applications engineer at Maxim Integrated. Over the years, I've helped a number of customers with their thermocouple designs, from monitoring kiln temperatures to measuring meat smokers. Today I'll be using the MAX31856 to show a quick and easy way of getting started reading temperature from a thermocouple. A thermocouple is a specific combination of different conductors that can be used to measure temperature. When one junction is at a different temperature relative to another reference point, a voltage difference develops based on the temperature difference. If the hot junction temperature or the cold junction temperature is known, the temperature of the other side can be calculated based on the voltage difference that develops. Thermocouples are a great way of measuring temperatures over very wide ranges, and some can operate up to 1500 degrees Celsius. There are a few design challenges when trying to measure temperature from a thermocouple. Because thermocouples can operate over such a wide range, the change in voltage for a given change in temperature isn't always constant, which causes thermocouples to be nonlinear. Additionally, getting a very accurate measurement of the cold junction is crucial to getting an accurate measurement of the hot junction. To see a few of the design challenges related to thermocouples and how to solve them, check out my application note, The ABCs of Thermocouples. The extremely popular MAX31855 was a great chip for incorporating both linearization and cold junction compensation. But the next generation MAX31856 improves on the original design with a few additional features. Improved EMI filtering, the ability to support all thermocouple types with a single chip, using a lookup table for increased linearization, and the ability to look at the raw thermocouple voltage itself. To show the chip in action, I'll be using the MAX32655 mbed board as my microcontroller and talking to the MAX31856 PMB1 board. I'll be using the SPI interface and supplying 3.3 volts in ground from my microcontroller board. The example code I'll be using prints the thermocouple cold junction and hot junction temperatures in a continuous loop to a serial terminal. The MAX31856 library, which was written by my intern Devin last summer, can be found at the link below. Once the program starts running and we're plotting temperature values to a serial port, I'm going to open up the Arduino IDE and use the serial plotter built into that, even though I'm not using the Arduino for programming, just so I can see a nice graphical representation of the temperature values. So if I pull everything up, you can see that so here the red trace is going to be the thermocouple hot junction temperature, and the blue trace is going to be the thermocouple cold junction temperature. Now I have with me some ice water and some hot water, and I'm going to plunge the hot junction tip into each one of those, and we should see a pretty big jump in thermocouple temperature readings. So when I put the tip of the thermocouple in the ice water, you can see that the external junction is approaching 0 degrees Celsius, which is what we should expect. And the cold junction remains at room temperature unaffected. Now if I take the tip out of the ice water and plunge it into the hot water, you'll see the readings jump up to about, looks like it's approaching 70 degrees Celsius. So you can see an example of the thermocouple reading hot and cold temperature. That's all for today. In under 5 minutes, I was able to show how to get temperature measurements from a thermocouple using the MAX31856. To see more about the part, go to the product page linked below, or check out the mbed library with example code. That's all for today. I'll see you next time.